Let's look at an example of a three-phase system that's unbalanced. It's unbalanced because of the load. The Y source will still be balanced, but so the line currents will become out of phase. The line voltages will still be in phase, and the phase voltages at the source will still be in phase, but the line currents will be out of phase. So there's going to be a voltage that will exist across the neutral line, but the wattmeters will still measure the power, so we'll take a look at that. So this example here, we want to find the power delivered to this Y source from this Y connected load, where we know the line voltage at the source, that's 100 angle 0 degrees from A to B. And we know these phase impedances at the load. We know that ZAN is negative J10, ZBN is positive J10, and CN is 10 ohms. So let's see how we can analyze this. First of all, what we do know is since the source is still balanced, our line voltages are still, we're going to assume positive phase sequence. I don't recall if it said that, but in positive phase sequence, then our BC will lag AB by 120 degrees, and our CA will lag AB by 240 degrees. So we still have the same relationship with the line voltages. We have the same relationship with the phase voltages at the source. That's going to be equal to the line voltage divided by square root of 3 angle 30 degrees, or divided by square root of 3 and then phase shifted. So our by negative 30 degrees. So our phase voltages lag our line voltages by the 30 degrees still. Okay, so that's still the same even though there's an unbalanced load. That unbalanced load given here, let's see how then we can analyze that. Since the load's unbalanced, what we really need to do is a mesh analysis to obtain the currents. So let's take a look at a mesh, how we can analyze this with a mesh analysis. So we have VCA, for example. Here's our VCA from here to here. Well, at VCA, if we look on this side, we don't have any line impedances. So if we did, we could just push them into AN, but this said there was no line impedances, or push them into CN. But between C and A, we have our AN and our NC. So we have these two impedances. So there's one mesh, and here we have our second mesh between A and B. Here, what we have is our AN in this direction and BN in this direction. So we want to make sure we draw this correctly so it's easy to then do our mesh analysis. So then now let's go ahead and do a mesh analysis on this circuit. We'll get our, as a result, we're going to end up with, for example, we'll end up with ICA. Well, ICA is not a line current, right? ICA is this current between here and here. And that is actually the sum of two currents. So if we look, we can look here at the mesh is the easiest place to look at it. So our ICA flowing into node A, we can say ICA is equal to IAN flowing out, IAN flowing this way, and IAB flowing to the right from node A. Well, what we want is our line current. If we want this line current IAA, well, IAA is the same as IAN. So that, that tells us then that our IAA, which is equal to IAN, that's going to be equal to our ICA minus IAB. So once we get these currents, from that, we can calculate our line currents. And then from our line currents and our phase voltages, we can calculate the power, which is what we want to do here, calculate the power of the three phases. So with that, we can also say that if we just look here at node B, our IAB flowing into node B is equal to IBN flowing out, and IBN is the same as IBB, right? They're in series, so it's equal to IBN plus IBC. So that gives us our IBB, which is equal to IBN is equal to IAB minus IBC. And then we can also get that our CC, which is equal to ICN, right? That's this, our ICN current is going this way here, so that's equal to our IBC minus ICA. IBC minus ICA. So let's go ahead then solve for these mesh currents. And now that we have this in a mesh, this looks very similar to us for us to be able to solve. And as we go through and solve, we do have to be a little bit careful. We do our meshes clockwise. So now when we do this first mesh, I guess we'll start here at IAB just because we typically do A's first. So in our IAB mesh, we end up with negative, we end up with a positive VAB because of this direction. And then we'll just add to that plus our this J10, right? We'll just write it out. J10 times our IAB minus IBC plus our negative J10 times IAB minus ICA. So when we go to simplify that, we get that for IAB, we end up with our 10 minus J10, right? So we have minus J10 and J10, so we get 0 IAB. And then we for IBC, we have minus J10 IBC. And then for ICA, I didn't put the parentheses there, we get minus J10 ICA. Let me just fix my writing. I was looking how I didn't put the parentheses there. So J10I, that's our IBC. And so that's all equal to, though, negative VAB because we're going into the positive voltage terminal. And let's just also correct this because I didn't simplify well. It was minus J10 but minus ICA, so that should become a positive. So that's for our AB mesh. If we go to our BC mesh, we're going to get, try to write a little bit smaller, VBC. And then we're for VBC, then we're going to get plus 10 times IBC minus ICA plus negative J10 times, whoops, no, that's a positive J10, we're going this way, positive J10 times IBC minus IAB. So I wrote that a little bit better. So that implies then that, so for our IAB, then we have negative J10, IAB. For our IBC, we're going to get positive J10, 10 plus J10, plus our 10 plus J10, IBC, and then for ICA, we just get minus 10. Minus 10 ICA, and that's equal to negative VBC. And then for our ICA mesh, again, we'll get VCA. We'll try to write this just concisely all at once. You can go through that method, but it's all going to be equal to negative VCA, and then we have ICA flowing through 10 minus J10 in the positive direction. So we're going to get 10 minus J10 ICA. We've got IBC flowing through the opposite directions through 10. So we got negative 10 IBC, and then we have our IAB flowing in the opposite direction through negative J10. So we have a negative of negative J10. So we get positive J10 IAB. So if we put that into a matrix format, then we have 0, negative J10, positive J10, and that's IAB, IBC, ICA, right? And for our second row, second equation, so it's a second row in our matrix, negative J10, 10 plus J10, negative 10. And of course, let's put it what it's equal to. So it's equal to, the first row is negative VAB. And if you recall, we were given back here, our capital AB is the same as lowercase ab because there's no line resistance. So AB is 100 angle 0 degrees. So we probably should write that up there. Our VAB is equal to 100 angle 0 degrees. Sorry to go wacky there for a minute. Okay, so this is then was so this is negative of that, so we can just write in negative 100. Give some space, and for negative VBC, so that means that our VBC, that's going to lag that by 120 degrees, so that's going to be 100 angle negative 120 degrees. So we get negative 100 angle, we'll just write it in as negative 100 angle negative 120 degrees for now. But really what we should do is we should add 180 degrees to that. That's equal to, you know, if we, so negative 100 angle negative 120 degrees. If we add 180, that's 100 angle 60 degrees. So that's, we could do it either way in the calculator, but this is the more appropriate way to write that. And then let's just write up here again our VCA. That's going to be our 100 angle negative 240 or positive 120 degrees. So our negative VCA is going to be equal to, we'll subtract 180. It's going to be equal to 100 angle negative 60 degrees. So we can put that in either way. We'll put it here, we'll put it, this is our preferred way to write a phasor without a negative magnitude. This is just negative 100, so we can write that with a negative number. All right, so let's fill in our third. That's J10, negative 10, and our 10 minus J10. 10 minus J10. All right, so you can put that in your calculator, solve it with MATLAB, solve it with another method, but let's get our results here. When we solve, we get that our IAB is equal to 19.32 angle negative 165 degrees, and that's amps. And we'll assume RMS, our IBC, that's equal to 10 angle negative 90 degrees amps, and our ICA is equal to 0. So we wanted to go back and we want to solve from that. We want to use that to solve for IAA, or which then is our IAN. Let's make sure those are correct. We have that IAN flowing out down this way. Do it in green. There's our IAN. That's equal to ICA flowing in, and then it should be plus this flowing out. So that's flowing out. So flowing in then we'll consider it a negative. So we subtract our IAB. So that looks good. So when we plug in what we solve for here, what we should get is that this is equal to 19.32 angle 15 degrees. This is equal to 19.32 angle 165 degrees, of course, RMS ampage. And then our ICC is equal to 10 angle negative 90 degrees amps. So what we want to do from this is we want to calculate the power. So so if we have that on this slide, we do have a potential difference across the neutral line, right? So our even though there's no wire there, there's a potential difference. Our VNN, that's going to be our VNB plus our VBB, and be in this direction, plus our VBB times J10, or IBB. IBB is this current here, right? So, which is the same as our IBN. So we do get this voltage here across the neutral wire. And again, our line voltages are all still the same, or phase and line voltages, because we have a balanced source. So if we go to calculate our power, then if we put in our wattmeters, our phase voltage, that was 100 over square root of 3, the line voltage divided by square root of 3 times our line currents, right? So we can use for PA, that's going to be IAA, so that's our 19.32. Our phase angle at AN, negative 30 degrees. Phase angle for IAA, negative 15. We get 788.7 watts. For PB, the VP is the same, but our VA or VBN, that's negative 150 degrees. It's negative 30 minus 120, and then our IBB current, that was that had an angle of negative 165 degrees, and then an amplitude of 19.2. And then finally for PC, when we add them all up, we end up with 1,000 watts. We can see, well, that actually makes sense, because if we go back and look at these loads, what we had here for our loads was that ZC was 10 ohms, right? This was 10 ohms, and our ZB, that was J10, and this was negative J10. So we had an inductive load here, the same reactance, same magnitude of reactance as our capacitive reactance in line N. So those two are not going to absorb any average power. So we just need to calculate IC. In this case, we just need to calculate our ICN or our ICC. So that's that ICC squared times the 10 ohms, and that's our 1,000 watts. So we can also do this with a 2-watt meter method if we place the common potential terminal. As we showed here, we place them at B, or excuse me, at B, so we can just use our 2-watt meters, and then we can show here with our numbers that our P1 is going to give us 6 watts, our P2 866. The sum of them will still give us 1,000 watts. So you can verify this with these numbers. The other key thing here is determining the power factor if the load is unbalanced. We can determine this power factor, and I'm not going to go through and prove this, but the tangent of theta z is the square root of 3 times the, with our two wattmeters, wattmeter 2 minus wattmeter 1 divided by wattmeter 2 plus wattmeter 1. So our power factor is going to be the tan inverse of that, right? So, but we find then if those two powers are equal, then we have a totally resistive load. We get a power factor of 1. If P1 is the negative of P2 here, then we're going to end up with 0 in the denominator. So that means we have a completely reactive load. And if P1 is greater than P2, we'll end up with a leading or capacitive load, so a leading PF, because this is going to be negative, right? And if it's positive, then we have a lagging or inductive load. That's if P1 is less than P2. So we can find out a lot from these power meters, and they can give us these results of our power factor as well as just our power. So that's it for this video.